First, let me welcome you to Physics 4010. Thanks for taking the course. I want to talk to you about some of the physics background in the Stern-Gerlach apparatus. Most of you haven't had a lot of physics like Physics 2010, even some Physics 1220, and I want to give you some of the background so that you'll understand what it's about and give you a better feeling of what we're discussing. In the Stern-Gerlach experiment, we have an oven that produces a gas of atoms. The atoms are neutral, they're not ions. And when they come spewing out of the oven, they pass through a collimator so that we have a beam of these neutral atoms. They pass through a magnet. And here in the cross-section of the magnet, you can see that it's not a uniform magnetic field. And when the silver atoms pass through the magnet, they start diverging from one another and form two spots on a detector screen. We want to understand what's going on with this setup. Well, first of all, neutral silver atoms, when you send them through a magnetic field, right, the electric force is given by QV cross B. But since Q is 0, these are neutral atoms, there's no such force. So that's not what's creating the divergence. So what is? Well, if it's not because of a charge, it must be because the atoms act something like magnets. Okay? So here's a picture of an electron going around in a circle, in a planar circle. And one of the first things we know about something like that is that it will have orbital angular momentum. Orbital angular momentum is given by the letter L in this textbook. Okay? Now, if the object is charged, then you have the equivalent of a current going around in this planar circle. And that gives you a magnetic field, which you would have learned in Physics 1220. And Physics 2420, you would have spent some time on that as well. And it turns out that the magnetic moment and the angular momentum, they're related to one another. So the definition of orbital angular momentum is mass times velocity times the radius of the circle. On the other hand, there's a simple formula that says a ring of current produces a magnetic field equal to mu naught I is the current, divided by 2 pi r. Now the current is Q over T. We don't have a real current. We've only got one electron going around in a circle. So it's one electron divided by the time it takes for an electron to go around once, which is pretty damn fast. And so that's actually fairly high, even though the electron is small. And this is the formula we get. Now, the definition of the magnetic moment of a current loop says that mu should equal to I times A. The direction is given to you by a right-hand rule, like so many things in magnetic properties. So in both the direction of L and the direction of mu, you use your right hand and curl it around the direction of the path. Your thumb points up. Okay? Now, taking the formula that we have here, that mu is defined as I times A, we see that mu is directly related to the angular momentum as well. There's a common definition of something called the Bohr magneton. It's sort of like a typical or fundamental amount of magnetic moment. It's E h bar over 2m. So the magnetic moment for this atom is mu b L over h bar. Okay. Let's move to the next page. Now, if something has a magnetic moment, it means it's acting like a tiny bar magnet. So here's my tiny bar magnet. The direction of mu is from the South Pole to the North Pole. Right? In this case, right, we've set it up so that the magnetic field is pointing in the z direction, and we use that to define the z direction. And to understand some of the formulas that we're going to use, we're going to directly compare the magnetic dipole to something that's a little more familiar to most of you, the electric dipole. Here's on the left-hand side is an electric dipole. You might recall that an electric dipole is formed when you have opposite and equal charges. The strength of the dipole is simply the magnitude of the charge times the length, and the direction of the electric dipole goes from negative to positive. Now, in an electric field, the positive charge is going to feel a force, and the magnitude of that force is Q times E. And the opposite negative charge is going to feel a force also of the same magnitude. This is a uniform electric field. Those two forces are identical to one another, so the net force is zero. On the right-hand side, we tried to show the same thing with a bar magnet. Now, one model of magnets is that they have something equivalent to charges called poles. There are no poles, but this model will get you pretty far along the calculations that we need. So this model, old model, but a useful model. So we've got a North Pole, and we say its strength is M, and a South Pole with strength is negative M. And by analogy with electric fields, the forces are the, quotes, magnetic charge times the magnetic field, just like F equals QE, F equals MB. So this is a useful model, right? But magnets don't have actual poles. We saw that a loop of current gives you this magnet. And so there's no actual pole. The magnetic moment is defined, pardon me, as M times L. Okay? So it's almost equivalent to the electric field, right? All the analogies are the same. Let's look at the torque on the dipole, right? We've got a force, right? We've got two forces, equal and opposite forces. That's a couple, if you were doing mechanics. And because of this, we can consider any point along the object and figure out what the torque is. So I'm going to do it about the negative charge. Okay? And the definition of torque is R cross F. So the distance would be L. The force would be QE at the end. Q is a constant, so I'm going to pull it over to this side. And we get the formula that the torque is equal to the product of the dipole and the electric field. Well, the same thing will happen when you calculate the torque on the bar magnet. You get that it's the magnetic dipole times the magnetic field. Okay? And the direction of the torque is at right angles. So what happens is that the torque leads to the precession of the bar magnet about the z-axis, which is what this diagram is trying to show. Let's talk for a little while about the energy of the dipoles in their respective fields. Okay? So this is the way that an electric dipole wants to line up in an electric field. Right? The forces, right, are such that this guy, right, positive wants to go towards that side of the electric field, negative to this side. It's stable. This is going to be the lowest energy state. Okay? The net force is 0, but it's stable. On the other hand, if I flip the two charges, the net force is still 0, but this is clearly unstable. So this is the highest energy state. Same thing if we look at the magnets, right? The North Pole wants to align with the electric field. The South Pole wants to go in the opposite direction. Okay? So one stable, unstable, we want to talk about their energies then. Okay, so I'm going to do it in terms of the electric dipole. The definition of work is the torque done on the object as it rotates through an angle. This is the appropriate version of the work because we're talking about rotation here. Okay, well, the torque we already found was P cross E, and doing that, it's the magnitude of P times the magnitude of E times the sine of the angle between them. Okay. This is an easy integral to do, and we get this formula for the definition of how much work is done. Now, since the work only depends on position, right, an initial and final position, that's a sign in physics that you can assign a potential energy. So we're saying our work has to be the negative of a change in potential energy, a U final minus a U initial, right? And then a minus sign in front of it, right? And when you break that out and you compare the two, what you get in general is that potential energy must be PE cosine theta. Or, and if you recognize that format, that just means P dot E. Right? This gives you that the potential energy is 0 when these guys go flat across the screen. Right? So when this angle theta is 90 degrees. And you can do the same calculations, identical calculations, and find that the potential energy of a magnet in a magnetic field is mu dot B. Okay, now, even though a neutral atom has a magnetic moment, it still feels no net force in a magnetic field. I didn't write that down, because the force on the poles are equal and opposite. Right? So this will precess, but it's not going to move anywhere. Right? It's not going to translate. Right? It doesn't feel any net force. It won't accelerate at all. Okay? What you need is a non-uniform magnetic field, as shown in this case, in which the forces are neither the same size and direction. Okay? Which is why back in the original picture of the Stern-Gerlach apparatus, we had a non-uniform field. Okay, so how much force does it feel? Right? Well, in mechanics, and various versions of this that you would have done in some of your vector calculus courses, would say that if you have a potential energy, and here's my potential energy, then the force is simply the gradient of the potential energy. Now, to simplify the setup, right, we chose B and the apparatus to be in the Z direction. So the only variation in B is along the Z direction. It's constant in the X and Y direction. And mu will only be a constant. So the gradient reduces in this special case down to mu Z, the derivative of the magnetic field with respect to Z. So neutral silver atoms going through a non-constant uniform magnetic field would feel a force, which is what we're expecting. Except if you think about it, neutral silver ions should not have a magnetic moment. It should be zero from what people understood classically about the structure of atoms. So it's a surprise. Okay? Let's look at why that should be a surprise. Okay, so why would we expect that the magnetic moment of silver, not other atoms, but silver for sure, should be zero? Well, if you look at the electron configuration and you go up through this, then there's all these filled orbitals, and then there's one s orbital. Now, the thing about these filled orbitals is that the filled orbitals in aggregate are spherically symmetric. Okay, but what about this 5s1? Well, quantum mechanics, so we're jumping ahead of ourselves, tell us it's a spherically symmetric orbital as well. Okay, so here are the s, p, and d orbitals showing the probabilities of where you'd find your electrons. Okay. So why is this guy spherically symmetric, and what is it about spherically symmetric that leads to mu equals 0? Well, think of a spherically symmetric orbit, like this shell of an orbital for the s orbital, and think of it as the electron going around many different ways, right? So that it's only spherical because it's made up of many plane orbitals. Well, on average, the arrows are going to have to cancel out, right? The magnetic moment and the angular momentum will end up being zero. That's why there's no expectation that a silver atom should have any type of magnetic moment. Maybe the protons and neutrons in the core, which people didn't really know much about at the time these experiments were being done, might have some magnetic moment, but the electrons shouldn't. And even if it was all the core had a magnetic moment, because the masses are so much bigger, the magnetic moment should be so much smaller, right? So one proton is about 2,000 times heavier than an electron. That reduces the fields, right? And the angular momentum, if we go back to this formula, right? If we look at the formulas for these guys, right? It depends on the inverse mass, right? So protons and neutrons should be way smaller. Okay, so what's going on? Well, lone electrons then must have some extra, what we call intrinsic angular momentum, and it's typically called spin because when a planet goes around the sun, it has orbital angular momentum, but it's spinning on its own axis, and that's usually called spin angular momentum. But I have to emphasize this point, right? Electrons do not spin. It's actually a quantum effect. Okay, so if all the electrons up here have spin, why is there no a lot more, right? Because I got all these electrons. Well, the way the electrons pin up in the pair up in these orbitals is one spin up, one spin down, and they cancel out, right? Symmetry says they cancel out. And you can see that if you go to the next atom after silver in the periodic table, which is cadmium, it's 5s2, it doesn't show any splitting. The two electrons, their total angular momentum, their spin angular momentum, cancel out, and it doesn't split. Okay, so there's a lot of physics going on in the spin-Gerlach experiment. Right? And so what the spin-Gerlach apparatus is doing, it's showing that there's this spin, and it's probing the nature of the spin of this unpaired electron. Now, how are we going to define the electron magnetic moment? Well, for orbital angular momentum, we said it was the Bohr magneton times its angular momentum divided by h. Well, that's the formula we're going to choose for intrinsic spin. L, well, it's now the spin angular momentum, not the orbital angular momentum. And there's a fudge factor in here, the gyroscopic ratio, which gets figured out, right? But we're going to ignore it. Just think of it as a fudge factor to make the formulas look similar to one another. We don't even need to know this value for most of the course. Yeah. Okay, so we've got this spin. What about the one last mystery? Well, we still haven't explained why there are two spots. So here's the oven again. Here's a beam of neutral silver atoms coming out of the oven, right? Now, because they're warm, they should have randomly oriented spins. A few should point straight up, right? I don't think I have any pointing straight up. Maybe a few pointing straight down, but the vast majority will have their mu's pointing in smaller angles. Okay? And so when they go through the field, what we should see is a distribution. A few of the spin ups up here, some of the spin downs down here, but the spins in between's the vast bulk of them. So you get some sort of bell curve or Gaussian distribution on your screen. So what's going on? Well, what Stern-Gerlach had discovered, they discovered the spin, and in a surprise, angular momentum, spin angular momentum, and later we'll see angular momentum in general, it's quantized. Just the way that, you know, people have discovered something about energy being quantized, right? They had discovered that angular momentum was quantized. Sometimes this is called spatial quantization because you see the spread of the particles in space. Okay? But it's this quantization that's important. And in particular, it's telling us that the Z component only has two possible values, plus or minus half of the Planck constant, h bar. Okay? If we tilted the Stern-Gerlach apparatus, there'd be another Z, we still only get two values. So no matter how you rotate the Stern-Gerlach apparatus, you only get two spots. You might recall that in the Bohr model of the atom, of the hydrogen atom, he had assumed that angular momentum was quantized. Appears that was a pretty good guess, right? And this experiment is showing that that's true. And in the Bohr model, when you quantized angular momentum, this was what led to the energies of the hydrogen atom being quantized. Another point I should just make, that we've talked about silver, and I also talked about cadmium having no lines. There are lots of atoms where the electrons will have both angular momentum, if they're in a p or a d orbital, right? And s angular momentum. And in those cases, you can get many more lines showing up in the Stern-Gerlach experiment. Anyway, that's what we want to know for now, or cover for now. Just some background to understand why the Stern-Gerlach experiment was so important. Right? So it's showing you about the spin of the atom, and the spin only has two possible values. That's it for now. Thank you.